we're covering today is waves. When I say waves, what comes to mind? Radiation, the ocean, Sophie doing this with her arm. Sound. Okay, what else? Okay, light, energy moving through a substance. Amplitude. So now we're getting terms about parts of waves. All right. So when we talk waves in physics, one of the big things that especially theoretical physicists like to play around with is the idea that anything that moves can have its motion approximated as a wave if you make what we call the wavelength long enough. So really, motion of particles or motion is a wave. So on a less theoretical physicist side of things, anything that moves energy from one location to another through cyclical patterns is a wave. Anything that moves energy from one point to another through cyclical patterns, patterns that are repeating or cycling, like that, is a wave. There are two large categories of waves: mechanical waves and non-mechanical waves, or electromagnetic waves. Electromagnetic are your things carried by photons, so radio, microwave, infrared, light, ultraviolet, X-ray, gamma rays. We'll talk about them more in depth later. For now, we're going to focus on mechanical waves. A mechanical wave is any wave that requires a medium in order to propagate. Any wave that requires a medium to propagate. Okay? So if we talk about sound as a mechanical wave, sound is a mechanical wave because if we go up into the vacuum of space and AJ starts screaming at us for some reason, nobody's gonna hear her because there's no medium for sound to travel through. So because of this, there is no sound. So a medium is simply a substance through which a wave travels. A substance through which a wave travels. So beyond just categorizing waves as mechanical and electromagnetic, we can also go further to categorize specifically mechanical waves as three different types of waves: longitudinal, transverse, and surface waves. We're going to start with the longitudinal waves because this is the one everybody pictures when they think of a wave. Yes. Longitudinal waves are any wave in which the particles of the medium travel perpendicularly to the direction of motion of energy. Any wave in which particles of the medium travel perpendicularly to the direction of motion of energy. Illustrated, this is a pretty easy one to visualize because it's what you get if you whip a rope up and down. Okay? You get something that looks like up and down motion. An individual particle on this wave is moving either up or down at some point. Okay? The further it is away from the medium, the slower it is, or from the rest point, the slower it will be moving. The closer it is to the rest point of the medium, the faster it is moving. Yeah, that's an end statement there. Okay. Say again. Yeah. All right. Within the longitudinal wave, there are a few different pieces we've got to be able to identify. First of all, the high points are what we call a crest. So that'd be here and here. The low points are what we call a trough. The height of the wave, meaning from the crest or trough to the rest point of the medium, is what we call the amplitude. Or I could draw that here. I do want to be very, very clear about this because every year on this test, somebody botches this. And I have a question where I ask you to label the crest, trough, amplitude, and wavelength. We'll get to wavelength. And every year, somebody draws a line from here to here and calls it the amplitude. No, that is twice the amplitude. Okay, fine, if you label it twice the amplitude. But if you label this full distance amplitude, you're wrong. Okay, amplitude is either crest or trough to the rest position. Good? Okay. Say again. Then it is still going to work out that way. We aren't going to deal with Fourier transfers of waves because that is definitely getting into the physics 3 realm, not physics 1. So, right, yeah, we're not going to do with Fourier transforms of waves, no. Although they're a lot of fun. All right, last one here, wavelength. The 9th grade definition of wavelength is from crest to crest or trough to trough. The real definition of wavelength is the distance between two identical locations on a wave. So that could be crest to crest or trough to trough, but it's also any other two identical positions. So from here to here, notably not here to here because this has a positive slope, this has a negative slope, these are not identical. So this has a positive slope, this has a positive slope at the same location, those are identical. Crest to crest, obviously, trough to trough, yes. But I could also pick these points. I could pick these points. I could pick these points here. You get the idea? Okay, go ahead. Other way, faster. Yep. Okay. We'll get to the exact position equations soon. And they're nicer than the calculus ones because mathematicians like to have every variable accounted for, and physicists say just move to 0. So you'll see it'll be much nicer than your calculus wave equations. All right, so just a few definitions. Crest, this is the high point of a wave. Trough, this is the low point of a wave. Amplitude, this is the displacement from the highest point to the rest position. Displacement from crest or trough to rest position. Wavelength. Wavelength is, as we said, the distance between two identical points on a wave. The distance between two identical points on a wave. Mathematically, amplitude is represented as A in meters. It's not area or, well, that's the only one. Area is the only one we've had. Yeah, that's a unit, not a variable in an equation. Wavelength in an equation uses the Greek symbol lambda and is also in meters. Okay. Crest, trough, amplitude, wavelength, those are the four we've got labeled on there because those are the ones that are like physical locations or distances. The next ones I really can't illustrate on a picture because they base on time. So our next one up is frequency. Frequency is the number of waves that pass a specific point per second. The number of waves that pass a specific point per second. Mathematically, it is F. I'd like to draw mine as a cursive F. I'm not entirely certain why. I'm sure there's a reason. I don't remember it. Okay, and is measured it's just kind of a loopy F. All right. Oh yeah, you're right. It's got that. Yeah. Yeah, it kind of does. Yeah. All right. It's a musical F. That's probably why I write it like that. All right. So it's measured in events per second. Rather than saying events per second every time we measure frequency, we alternatively measure it in hertz, which is equal to 1 hertz. So if we talk about something that happens 9 times per second, we're talking about something that has 9 hertz as its frequency. Okay. Let's see here. And then I need period. The period of a wave is the amount of time it takes one wave to pass a single point. The amount of time needed for a wave to pass a single point. In equations, it's a capital T, which we have actually seen before. We've seen capital T in Kepler's law, which we saw as orbital period or length of year. We also saw a capital T somewhere in rotation. I can't remember where. But again, it was just representing the time for one event. Okay, so period is capital T. This is also measured in seconds. And if you look at the definitions between frequency and period, you notice that they have a lot of similarities. In fact, they're kind of just inversions of each other, meaning that the relationship between frequency and period is simply period is equal to 1 over frequency, or vice versa. Questions to this point? Wave speed depends only on the quality of the medium. Depends only on the medium. You say the speed of sound is constant, but our lab later this week is how does the speed of sound change? And I'm going to save the when you do what portion for later this week. Oh, no, we're not going to go into water. No. We're going to do it in how does the speed of sound in air change when? All right. I think it's going to be Thursday or Friday. I'll have to take a look. Should be. Maybe it's next week. All right. So wave speed. Calculate speed of a wave. Speed of a wave is, well, if wavelength is measured in meters and frequency is events per second, then if I simply multiply wavelength by frequency, I get meters per second. So wavelength times frequency. All right, so we've got crest, trough, amplitude, wavelength, frequency, period, wave speed. Questions on any of those ideas? So each of these has an analog into the other types of waves. This is just for longitudinal waves. Our next one, or, oh my gosh, I mislabeled this. I'm so sorry. This is transverse. Did I write that anywhere else? No, it's the only place I wrote it down. Yep, those are transverse waves. Transverse literally meaning lying across, where the different parts of the wave lie across the direction of the motion of the energy. Everything's still accurate. It's just that one word that I misused. Okay? No, I've got nothing here. Yeah. Since that was actually transverse waves, now we're going to talk longitudinal waves. For real now. When I'd suddenly, hey guys, if you haven't seen this yet, I changed that. All right. Longitudinal waves. A longitudinal wave is a wave in which the particles of the medium move parallel to the direction of motion of energy. Any wave in which particles of the medium travel parallel to the direction of motion of the energy. Of motion of energy. All right, so drawing this one out is way more interesting. Rather than just being a nice sine curve, the only ways I can really draw this are either trying to simulate air as a density wave or with the Slinky. I'm going to go ahead and just try drawing with the Slinky, where we're looking rather at portions of the Slinky where it is stretched or compressed. So drawing the Slinky out. No, they're not supposed to be the same. Hopefully, those look like they're tighter together, and those look like they're tighter together. Those look more spread out, and those look more spread out. Yes? So I'm actually going to label those sections. A section where they are more compressed is a compression. So I'm going to label these two segments as compressions. And these segments that are less compressed are what we call rarefactions. Yeah, it's one word. Rare meaning like not frequent, faction meaning like portion. So it's a low density portion. Crests. If you want to analogize the compressions to the crests and the troughs to the rarefactions, that analogy makes sense. And we'll actually see how compressions and rarefactions can translate into troughs and crests in 2 weeks. Oh, we're going to do it with fire, though. Yeah. We're going to make fire waves based on this. Yes, yes. All right. So a rarefaction is a low density area. A compression is a high density area. Longitudinal waves do not have crests or troughs. Amplitude, we could try to talk about, but it would really be more of a density difference between air without the wave in it and the compression or the rarefaction. So we're not going to deal with an amplitude. Wavelength, frequency, period, wave speed, all the exact same. Okay, so amplitude in a longitudinal wave is a particle density measurement. And then wavelength, frequency, period, wave speed, all the same. If we wanted to measure wavelength, we're going from compression to compression, we're going from rarefaction to rarefaction, or any two identical points within the wave. Caroline. You mean like this? Oh, on a longitudinal wave? Okay, so I'm not going to draw it like that because that tries to show the particles moving incorrectly. That would show the particles moving up and down, which they don't. Particles in a longitudinal wave move like this. So they use that drawing to try to get the illustration of what the amplitude is conceptually. However, it does lead, I've seen it lead to misconceptions in that a particle moves this way when in fact they don't, they move like this. Yeah. I'm not going to draw that because I think it's misleading. Say again? That probably is the case. They probably are using it as an energy demonstration. Habiba. Yes. In a standard wave that you're holding one frequency, yes. My drawings are limited. So yeah, compression would be the same size as a rarefaction in terms of their width, and it would be, density would vary as a sine curve. So in a transverse wave, the particles are going like this. Okay? In a longitudinal wave, they're going like this. I'll demonstrate that in just a moment. It's totally going to be the slinky again. Okay? Yeah. Or compression to compression. No, that'd be half a wave. That'd be like measuring from crest to trough, not from crest to crest. You could, if you also indicate that the particle has the same velocity, because yeah, you can. If you wanted to find the a wavelength as between two particles with the same velocity, that's appropriate because we'd be looking either at going up or down versus going left or right. Yeah, that would work. Habiba. Yeah, yep. So like a particle here would start moving up, slowing down, stopping, slowing down, coming up, slowing down, speeding up, slowing down, as just, yeah, that would be. Yes. Yes, I believe that, yeah. And then for a longitudinal wave, it would be like speed up, slow down, speed up, slow down, speed up, slow down, as it moves just back and forth. Okay. All right, so demonstrate. The last type of wave that we have to define today is a surface wave. A surface wave combines the motion of a longitudinal and transverse wave to cause the particles of a medium to travel basically in circles around an equilibrium point. Combines the motion of a longitudinal and transverse wave to cause particles of a medium to travel in circles. Particles of a medium to travel in circles. The best illustration of this is if I take a bobber. Anybody fish? Like, yeah, I know. I was waiting for it and then he wasn't here. So, hi, Marvin, this is for you. Me too, kind of. So, we've got waves on a pond. So, I want to point out a couple of things here. First of all, when I'm talking about waves on a pond, I'm not talking about current. Current is a different concept than a wave because current is the actual motion of the water itself moving from one point to another. A wave is energy within the water causing back and forth motion, up and down motion at the surface. Okay? So if we watch a bobber on a pond, not a river or a stream or anything like that, the bobber, when a wave goes by, moves both up and down and back and forth. But unless there's a current, it's not going to make progress one way or another. It's just going to circle around as the wave comes underneath it and then passes by it. So the bobber represents a particle of the wave medium as the energy is simply moving forward. So the wave moves forward, but the bobber stays in place. It's more ovular, typically. It depends exactly on the amplitude in terms of height. So you'd have to mix the amplitude of the transverse wave with the wavelength of the longitudinal wave to determine exactly what its shape would be. Said you didn't get it? So do you agree with me that the height of the water changes as the wave goes by? Okay, so that means the bobber's going up and down. So if the wave is going this way and the bobber is going up and down, those two things are perpendicular and therefore we have transverse waves. Okay, so as the wave goes forward, the water itself gets pushed back and forth. You can see this if you stand on a shore when waves are coming by. And you'll see the waves come up, wash back out, come up, wash back out. That's because there's longitudinal motion where the particles are moving back and forth with relation to their still position. This typically occurs, we get really two examples that are really good ones. It occurs anytime a wave occurs between two mediums. So water is a good example because the wave occurs where water meets air, two different mediums. We can also see this for seismic waves, where earth meets air. So we see ground actually ripple up and down for strong earthquake or seismic waves. So seismic and water waves.